We're asked to use Green's theorem to evaluate the line integral along the curve C of the vector field f dotted with the unit normal vector n ds. And this is the flux of the vector field f along the curve C, where C is the boundary of the region enclosed by y equals 4x minus x squared and the x-axis oriented positively. Looking at the graph, the vector field f is graphed in blue and the curve C is graphed in red with a positive orientation. Let's review the flux form of Green's theorem. To apply Green's theorem, C must be a simply connected piecewise smooth curve oriented counterclockwise that encloses the region R in a plane. If the vector field f has x and y components with continuous partial derivatives, then the line integral, which gives the flux, is equal to the double integral over the region R div f differential a, which is equal to the double integral over the region R of the partial of f with respect to x plus the partial of g with respect to y differential a. And again, this is called the flux of the vector field along the curve C, and it measures the flow moving across the curve C. It is similar to Green's theorem, except the flux integrates the perpendicular or normal parts of the vector field, while Green's theorem integrates the tangential part of the vector field. This is also referred to as the divergence theorem in a plane. So going back to our question, I do want to point out one thing before we set this up. If we take a look at the differential form of this line integral, notice how we have f dy minus g dx. If we take a look at Green's theorem just for a moment, notice how in differential form we have f dx plus g dy. This is the reason why the difference of these partial derivatives is different in Green's theorem than it is for the flux form of Green's theorem, as we see here. Looking at the vector field f, notice how the x component, which we'll call little f, is equal to, let's write this as x to the 1/2 plus 3y, and little g, the y component, is equal to 2x plus 3y. And now we need to find the partial of f with respect to x and the partial of g with respect to y. Looking at f, the partial of f with respect to x is equal to 1/2 times x raised to the power of 1/2 minus 1, which is negative 1/2. The derivative of 3y with respect to x is 0. And now for the partial of g with respect to y, the derivative of 2x with respect to y is 0. The derivative of 3y with respect to y is 3. Which means the flux, which is equal to this line integral, is equal to the double integral over the region R of the partial of f with respect to x plus the partial of g with respect to y differential a, which is 1/2 x to the power of negative 1/2 plus 3 differential a, where the region R is the region bounded by the curve C. For differential a, let's use dy dx. So this is equal to the double integral of 1/2 x to the negative 1/2 plus 3 dy dx. And now to determine the limits of integration for y, notice how the region R is bounded below by y equals 0 and above by the curve y equals 4x minus x squared. The limits of integration for y are from 0 to 4x minus x squared. And now for the limits of integration for x, we integrate from 0 to 4. Let's evaluate this on the next slide. We first integrate with respect to y, treating x as a constant. The antiderivative is the quantity 1/2 x to the power of negative 1/2 plus 3 times y. And now we need to find big F of b minus big F of a by performing substitution for y. This will give us the quantity 1/2 x to the power of negative 1/2 plus 3 times the quantity 4x minus x squared minus 0, which is just 4x minus x squared. Now let's go ahead and multiply. We'll have 4 products. This works out to 2x to the 1/2 minus 1/2 x to the 3/2 plus 12x minus 3x squared. And now we integrate with respect to x. the antiderivative is 2 times x to the 3 halves divided by 3 halves, or 2 times 2/3 times x to the 3 halves, minus 1/2 times x to the 5 halves divided by 5 halves, or 1/2 times 2/5 x to the 5 halves, plus 12 times x squared divided by 2, minus 3 times x to the 3rd divided by 3. Let's go ahead and simplify this. We have 4/3 x to the 3 halves. Minus simplifying here, we get minus 1/5 x to the 5 halves, plus 6x squared minus x cubed. Let's go ahead and finish on the next slide. We first substitute 4 for x, so we have 4/3 times 4 to the 3 halves minus 1/5 times 4 to the 5 halves plus 6 times 4 squared minus 4 cubed. And when x is 0, all the terms are 0. This simplifies to 32/3 minus 32/5 plus 96 minus 64, which is equal to 544/15, which is approximately 36.2267. Now remember, this is the flux of the vector field along the curve C, and the flux measures the flow moving across C. So because this value is positive, this tells us there is more flow passing through the curve C away from the region R rather than passing through C moving toward the region R. And the vector field does verify this result. I hope you found this helpful.